Hello, everyone. I'm Tommy Murphy. I'm at Cal State Fullerton in California, and welcome to my mini course on rigidity and instability for SUN symmetric spaces. So first off, just let me thank Huju for all the excellent work organizing the Geometric Analysis Festival. The other talks are great, and I'm really looking forward to watching them all. So here is an outline of what I'm going to talk about in this mini course. I've sort of split things into 3 talks. So the first talk, I'll mainly discuss the main results and do some preliminary material concerning Ricci flow. And then in the second talk, we will discuss sort of survey relevant results from concerning instability for low dimensions and for symmetric spaces. And that will naturally lead into a discussion about theorem B. So I'll explain the main theorems in a sec. And in the last talk, then we'll discuss the moduli space of Einstein metrics. And this is concerning the theorem A and further applications. So somehow this talk will concern rigidity, this talk will be about instability, and we'll state the main results and how these 2 topics are connected in the first talk. That's the plan. Everything I'll say is contained in these 2 papers. This paper just appeared in the Journal of Geometric Analysis, joint with Hall and Waldron. And this is the paper about instability, and we then realized that it's closely connected to rigidity, and in this project where we brought Wafa Batat on board as well. So everything I'll say is every theorem is contained in these papers and due to these co-authors, of course, as well. All right, so let's dive in. So the first main theorem says the following thing. It says that SU2n+1 is rigid. So firstly, when I say something is rigid, when I say SU2n+1, I mean this is a Lie group, but whenever I write down a homogeneous space, unless I say otherwise, I mean a symmetric space. So in particular, I'm viewing this as a Riemannian manifold equipped with the bi-invariant metric. Being rigid means that you can study the moduli space of Einstein metrics, and it's saying that it's isolated. In other words, there's no Einstein metric sufficient, like nearby in a sufficiently small neighborhood. So here, for example, we have the moduli space of Einstein metric of metrics of volume 1, and the question you're interested in studying rigidity is: here's your Einstein metric. Can you construct a curve of Einstein metrics passing through that point? Okay, so the answer is no for this symmetric space. Obviously, this is I guess I would say a foundational question. I mean, there's a large literature about this, and it goes back many years. But people, even for very straightforward examples of Riemannian manifolds, like a Lie group with a bi-invariant metric, it's still an open problem to determine whether or not the canonical metrics are rigid. So this is our contribution in this direction. Just a few remarks about why, you should care, right? So this theory was largely developed by Koizo, who came up with a very interesting example. So his example was the Einstein metric on CPn cross CP1. And he showed that this metric is rigid, or it's isolated, so there's no Einstein metric nearby. But he also has this infinitesimal description of the moduli space, which is described by these objects called EIDs, essential infinitesimal deformations. And so if you have no EIDs, then it's trivially rigid. The interesting question is when there are essential deformations. So that means that there are directions which to first order look like deformations through a curve of Einstein metrics. In that situation, does such a perturbation correspond to an actual smooth curve of Einstein metrics passing through that point? That's the sort of question. And that's why this is a very well-known example, because this manifold does admit essential infinitesimal deformations. So it has this infinitesimal structure which looks like it comes from a curve of Einstein metrics passing through the point, but nevertheless the metric is isolated. Okay, so our theorem is I think the first example since Koizo's of an Einstein manifold that's rigid but still admits EIDs. Okay. So that's really that's theorem A, and that's what we'll really be talking about in the third talk. The other main theorem we'll talk about is the following theorem, which is concerning what you would think to be sort of an unrelated topic. This is maybe a much more recent avenue of research, which is to do with instability under Ricci flow. So again, here we're looking at this manifold. This is the Grassmannian of the complex Grassmannian of K-planes. That's a symmetric space. You can give it a natural metric in making this a symmetric space as a Riemannian manifold. And the question we're interested in here is, you see Einstein metrics are fixed points of the Ricci flow. And if you think about any sort of dynamical flow, there's this natural questions to do with index and stability. So if you perturb from a fixed point, do you go on and run the Ricci flow? Do you run back to where you start to the fixed point, or do you flow away? Sort of a foundational question. And there's a huge literature about this now. And so this proves a large family of symmetric spaces are unstable under Ricci flow. Sort of to put this in context, if you take K to be 1, then the Grassmannian of 1 planes in Cn is CPn. And this proves that CPn is unstable when n has to be bigger than 1 for this to work. Because CP1 corresponds to the 2-sphere, which is stable. And I'll explain a little bit about those numerics in the second talk. This is a result of Krönke, and later there was contributions by Knopf and Shesum, who worked on this, who gave an exposition of his ideas. So, okay, so showing that CPN was unstable under Ricci flow was kind of I think a surprising result, because somehow people thought of CPN as the complex analog or Kähler analog of a sphere. And this is a generalization of this because it works for much more values of K. However, I would also point out it's sort of an intrinsic proof, because this proof uses the Hopf vibration, so it translates it up to a question about a sphere. And of course, we don't have where things are somehow more tractable, and we don't have such a general approach for general. I mean, this doesn't work for general Grassmannian. It's more complicated, and so somehow we have this unified approach which works for all of the Grassmannians included, so which is nice. Okay, so there are the two main theorems where I will sort of discuss the proof in depth. Now, this theorem is about instability, and the previous theorem is about rigidity, and the third theorem is where we sort of realize that these topics are connected. So suppose we have M is just the dimension of my manifold. We have an Einstein manifold. So the Ricci tensor is this multiple. For historical reasons, to do it agreeing with the rest of the literature, for stating this theorem, I'll write the Einstein constant this way, 1/2 tall. Now suppose I take an essential, an EID. So one of these deformations which come from the work of Koizo. So in particular, all we need to know for stating this theorem is that that's a symmetric 2 tensor. And so you can actually vary the metric by adding on just small multiples of H to S to G. Okay. And the theorem says that the third variation of the new functional, which is something going to be intimately linked with understanding stability under Ricci flow, is up to a constant depending on the dimension, the same thing as this quantity I of H. Now, I haven't explained what this quantity is yet. That's going to be in the third talk. But this is an obstruction to integrability, and somehow showing that this is non-zero is connected to is how you prove that things are. This is your obstruction to integrability, and this is how you prove that spaces are rigid. So this gives you a connection, which I'll explain in the third talk more detail, between rigidity and instability. That's why the two talks sort of go together, the two topics. If I have a little time in the last talk, I maybe will just connect this. Like, one of the nice things about our approach, I believe, is that we can connect together various different results in the literature in a kind of a nice coherent framework. So for example, we can reprove the result of Sao and Hay, that SUN is unstable under Ricci flow under our framework. And another example of this is that the Fubini study metric is isolated. You can study the moduli space of Ricci solitons, and we can show that this is isolated. This is a theorem due to Krönke, but we can sort of show it in our framework as well. Okay, so they're the main results. The main focus is going to be on theorem A and B, and explaining exactly how they work. And theorem C is sort of showing you that these two problems are connected. Okay, so now I'm going to discuss a little bit some preliminaries which are going to be useful throughout the talk. Firstly, we're going to take throughout the talk, our manifold will always be closed, connected, simply connected, etc., and a Riemannian manifold. The class of manifolds, Riemannian manifolds, we're really going to study are symmetric spaces. The most natural definition of a symmetric space is to say that the Riemann curvature tensor is parallel with respect to the Levi-Civita connection. For us, it's more convenient to have a description in terms of Lie groups. One way of showing that a manifold is a Riemannian symmetric space is to say that there's a subset of the, so there's a group G, which is a subset of the isometry group, which is acting transitively. And if you pass to the corresponding Lie algebras of G and H, they satisfy these relations. So somehow, the study of Riemannian symmetric spaces collapses to this problem at Lie algebra level. A simple example to bear in mind is the two-sphere. So the two-sphere you can geometrically realize by, you can pass from any point on the two-sphere to any other point by taking a rotation in three-dimensional space. So this is a transitive action. And okay, what's the stabilizer? Well, if you take the North Pole, say what's the stabilizer of the North Pole? There's a whole circle you can rotate around that fixed axis. So this gives you a description of the two-sphere as a homogeneous space. And if you pass to Lie algebra level, you include SO2 like this, the isotropy like this, corresponding to say the North Pole, you can check that the complement, so with respect to say the killing form, is given by matrices of these forms, where X is a 2x1 matrix. And then you can explicitly verify the bracket relations here. So this is a very rushed discussion of what a symmetric space is, I guess. But these are the manifolds that we want to focus on and study. To paraphrase, as Berger says, that the symmetric spaces are like pandas in the zoo of Riemannian manifolds, because they're the best, right? And so somehow they're the nicest, the most beautiful Riemannian manifolds. They're sort of the pinnacles of Riemannian geometry, and you want to understand everything about them. They're the first family of examples which are geometrically interesting, admit a wide variety of behavior, but still you can actually compute quantities for them. That's really what this talk is all about. Okay, so here are some useful references. The standard reference about symmetric spaces is Helgeson's book. But that's, there's a very nice, Wolfgang Ziller has really nice lecture notes about symmetric spaces and representation theory. And there's also books due to Wolf, Luce, Eschenberg has nice notes as well, which are good to read. Okay, so we're going to work on symmetric spaces, and they are specific examples of Einstein manifolds. So for the rest of the mini course, GE is going to denote an Einstein metric. And that's defined as a Riemannian manifold whose Ricci tensor is a constant multiple of the metric. So I'll take this number is called the Einstein constant lambda. We're always dealing with closed manifolds, and we will always be dealing with positive Einstein constant as a result. So the Ricci flow is, of course, the center of much current investigation, and that effectively evolves the metric via the Ricci tensor at each point t, where you start at your initial metric G0. It's standard to normalize the Ricci flow. This is the normalized Ricci flow to take into account. So if you run the Ricci flow on the sphere in finite time, it will shrink to a point, and you normalize it to avoid this type of behavior, and then you study what are the fixed points of this flow. And the fixed points of normalized Ricci flow come out to examples of them are given by Einstein metrics. So from this perspective, Einstein metrics were studied before this as a natural equation coming up from physics, from relativity theory, but also just as from a mathematical perspective. Of course, you could say this is a very natural and elegant condition to study. Okay, so our focus is on the case where the Einstein constants are positive. So we want to talk about stability, and here's the formal definition. Effectively, we're going to say an Einstein metric is dynamically stable if whenever you take a small perturbation, so you start at some point in a sufficiently small neighborhood around GE, and you start the Ricci normalized Ricci flow, then you're going to converge back to an Einstein metric. Notice here I say an Einstein metric, not GE. That's actually related to the issue of, is your Einstein metric isolated, or is there a curve of Einstein metrics passing through GE? Because we're going to be proving instability, it's going to turn out not to matter which there's some sort of varying definitions of dynamical stability, but it doesn't matter for us because we're proving things are dynamically unstable. So if it's not stable, we say it's unstable, okay, which means that you can move in a certain direction, move to a nearby metric, start the Ricci flow, and you're going to flow away and not come back to not stay inside this neighborhood. The first example is you take the product of two Einstein manifolds, say, compact Einstein manifolds, and you take a perturbation which inflates one factor slightly and shrinks the other one. So if you run the unnormalized Ricci flow, say you start with two spheres, which are the same size, and then you inflate one factor, inflate one sphere and deflate the other sphere a little. Well, then this has more curvature because it's a smaller radius, say. And so if you run the flow, this is unnormalized, this is going to shrink down quicker than this one. And so when you renormalize, this is going to show you that you must be moving away from the initial metric. So this gives you an easy example that you can sort of see of instability. It's a foundational example. Okay, so to study stability, Perlman introduced his W and U functionals. I used to always start my talks by giving like the definitions. And, you know, I don't really think you would get so much from seeing the definition if you're just getting an overview of what's going on. For us, all we need to know is that somehow a functional, which is defined on your space of metrics and outputs a real number, and its key property is that it's monotonically increasing under Ricci flow, unless you're at critical points. And the critical points are exactly what are called gradient Ricci solitons. So that's exactly where the Ricci tensor, so there's a function f on your manifold, so that the Ricci tensor plus the Hessian of f is a multiple of your metric. Einstein manifolds, of course, correspond to f being 0, and this term drops out, and you get Ricci as a constant multiple of your metric. So many people have worked on stability, and in particular in recent years, Knopf, Chessum, Bolzano, Hasselhofer, Krönke have worked on it, and somehow there's a very nice characterization of when a compact Ricci soliton is stable. So it being stable is equivalent to being a local maximizer of the new functional. One thing to say is, of course, the implication that it's a maximizer implies stable is immediately going to follow from monotonicity of the functional. So if it's a maximizer, strict maximizer, say for simplicity, and you perturb a little bit, well, because you were at a maximum, if you perturb sufficiently small, a local maximum, if you perturb a little bit, well, then the value of the new functional has gone down, and it wants to go up because it's monotonically increasing, so it must go back towards the local maximum. And so you must stay inside that neighborhood. So that's easy to see. So if we're at a critical point, what we want to do is compute the second variation of nu. And for the case of Einstein metrics, this was computed by a foundational paper due to Sau, Hamilton, and Nilmanen. To simplify their formula, they did the following. They took the following simplification. They worked with the space of, so sections of the elements of S2 of Tm star, so symmetric two tensors on the manifold. And this is really should be thought of as sort of a choice of gauge or something. So choosing the divergence to be 0 and choosing the integral of the trace to be 0. So this effectively is sort of being orthogonal to G, right? This is what, because if you take the inner product of G and H, you get the trace. And so this is somehow saying that the direction you move in is different to the direction you're at. And then choosing it to be divergence free, you can rewrite that in terms of a Lie derivative and of the metric. And so this is effectively up to choice of diffeomorphism. So that's what I mean by choosing the right gauge. Okay, you can satisfy this condition, and you're only it's effectively choosing the right gauge to simplify computations. It doesn't change anything to do with the new functional. Okay. So for perturbations inside this family, curdive 0, they computed the second variation and they get this really nice formula for, I mean, there's a strictly more complicated formula for Ricci solitons, but for Einstein manifolds, it effectively turns out to be this operator n, which is the, up to a constant, it's the Legnerwitz Laplacian plus twice the Einstein constant acting on H. So, right. So what we are interested in doing is saying, somehow you can see that the behavior of the second variation is going to be determined by the by understanding, say, for example, eigentensors of the Legnerwitz Laplacian. Okay. So, for example, if we can prove that this quantity is positive, then we're proving that something is dynamically unstable. This is an important point in what we're going to do, because this is called being linearly unstable, because these are linear perturbations. And I'm claiming that if it's linearly unstable, it's dynamically unstable. So how does that work? Well, if you move in a direction so that the second derivative, I mean, loosely speaking, if you move in this direction so that the second derivative is positive, so the first derivative vanishes because you're at a critical point, the second derivative is positive, that says that the critical point basically was a minimum of the functional. Okay, so if you move a tiny bit away in this direction, the output of the function has gone up. And so then if you start nearby and run the Ricci flow, there's no way you can flow back, because the Ricci flow, the new functional increases under Ricci flow. So it can't go back because it will be going back to a minimum. The new functional will be getting smaller. And so if you run Ricci flow, you must flow away. That means you've shown it's unstable. So that's a slightly, quick exposition of why, but this effectively is the reason why. Showing that this quantity is positive will prove, so this is called linear instability, will prove dynamical instability. Okay, so in particular, if we let kappa be the largest eigenvalue of the Legnerwitz Laplacian, in situations where kappa is bigger than minus twice the Einstein constant, I should say all my, I will adopt the convention of having negative eigenvalues. So if kappa is bigger than minus twice the Einstein constant, then you see this quantity will be positive. And then by the argument I just said, that will prove that will be called linearly unstable, and linearly unstable will imply dynamical instability. If it's below this threshold value, this is called being linearly stable. And this was analyzed by the work of Shesam, who showed under some mild integrability assumptions. So here we see a connection already with integrability in the moduli space of Einstein metrics. If you're linearly stable, you'll be dynamically stable. And so really the interesting threshold case is when you have this neutrally linearly stable case. So when you have an eigenvalue, the largest eigenvalue of the Legnerwitz Laplacian is exactly minus twice the Einstein constant. Okay. So that is the end of the first talk, and some sort of brief survey of what stability is and what it means for an Einstein metric to be unstable. So in the next talk, if you care to join me, I'll discuss exactly sort of what's known about this question and about instability for some for the basic examples of Riemannian manifolds, and we'll see how that leads into Theorem B, to proving it for the complex Grassmannians. All right, thanks very much for watching.